Hi, this is Mr. Zarzak, and in this screencast, I'm going to add these two vectors using the component method. Okay, so we have vector S and we have vector D. Both of them have the same magnitude of 4 meters, so these are displacement vectors, but vector S points 30 degrees above the horizon. Okay, so first thing I'm going to do is I'm going to draw my components for vector S. So the arrow points up and to the right, so the components point up and to the right. All right, so there's this one. And this one. Okay, I'm going to put my arrowheads on here, and then I'll label these. This is vector S sub X, so the horizontal component of S, and S sub Y, the vertical component of S. If we look at vector D, okay, vector D is completely horizontal, and so really this is just D sub X. And just so you're used to it, sometimes you'll see this written to communicate to the reader that there is no vertical piece to this. Occasionally you'll see the convention used where somebody will draw a little arrow and then just write dy is equal to 0. Okay, and again, that's just to communicate that there is no vertical component, that this dx is exactly sideways, not half a degree above the horizon or below it. Okay, but the x part really does tell us that it's horizontal. So I just want you to be aware of the notation. Okay. All right, so then down below, I'm just going to take and make myself some space to work. Okay, the battle with this is staying organized. Okay, so starting with my vector S for the vertical component, S and X. Okay, so I'm given this is like the hypotenuse of the triangle, right? And then this piece over here would be the opposite piece. In other words, it's on the other side of the triangle from the angle. Okay, so the trig function that relates opposite and hypotenuse is the sine function. So to solve for it, I just take, let me switch back to my red pen. I just take the magnitude of my vector S. There we go. And then multiply that by the sine of the direction theta. Okay, so Sy is equal to 4 meters times the sine of 30 degrees. And this winds up being 2 meters. Okay, if I do the same thing for the horizontal component, S of X, again, that's the hypotenuse. The piece next to the triangle, that's the adjacent. So the trig function that relates together adjacent and hypotenuse is the cosine function. So to get the horizontal component, I take the magnitude S and I multiply that by the the cosine of the direction. So cosine theta, just like that. Okay, so sub into my numbers. Sx is equal to 4 meters times the cosine of 30 degrees. And so Sx will be equal to 3.464 meters. Okay, when I do these, just like on WebAssign, I always go to 3 spots after the decimal before I would enter in a number. This is going to prevent any rounding errors that would occur when WebAssign is accepting answers plus or minus 1%. So it's just kind of a general rule of thumb. Okay, so I'm just working this like the way that you'd work a WebAssign problem. Okay, so if I look over at vector D, okay, I already do have my components. If you need to see the math on why dy is 0 and why dx is 4, that's no problem. We can do that too. So I'm just going to switch over to blue. All right, so by the same process, okay, my vertical component of D is just the original vector times the sine of the angle. Okay, and so if I subbed in dy would be equal to 4 meters times the sine of 0 degrees. Okay, and you may know this already, but the sine of 0 is just 0, so there is no vertical component of vector D. Okay, and again, just so we can see it, if I wanted to do dx, I would just go d times cosine of theta, and so dx would just be 4 meters times the cosine of 0 degrees. The cosine of 0 is actually 1, so we were really just taking 4 times 1. So the horizontal component is just 4. Okay, so I've got all my pieces here. Now, what I also like to do, okay, is when we work on these problems, okay, our choice for positive directions, this is a 2-dimensional problem, so I'm going to make up and right my positive directions. Okay, and I'm just going to take a quick peek here. Okay, so SY points up. Okay, and SX points right. dy doesn't point anywhere, and dx points to the right. Okay, and so the reason I go through and I do this step is because if any of these components happens to point either down, I can't spell either, or to the left, well then I just go and I change the sign to a negative sign to indicate the direction with my numbers. Okay, so now once I've done this step, okay, well then the next thing I need to do, okay, is I'm going to compute what's called the components of the resultant. Okay, and so all that means is the resultant vector, which I'm going to call R, has a vertical component and a horizontal component. To get the vertical component, I just take the individual components. So in other words, I take my value for SY, and then I'm going to take that and I'm going to add that to the value of dy. Okay, so if I go and put this together, Ry is equal to 2 meters for SY plus 0 meters for dy. So the value of my Ry is just, well, 2 meters. Okay, same logic. I'm going to do the exact same thing for Rx. So Rx is just the sum of the horizontal component of S added to the horizontal component of D. So Sx plus Dx. Okay, so looking at my table over here, so Sx was 3.464 meters, 3.464 meters, and Dx is 4 meters. So Rx is just going to be equal to 7.464 meters. Okay, once I have these pieces, all right, the next step, and this is an important one, so don't skip this, is I'm going to draw a picture. See, because Ry is a positive number, that means that Ry points up, and because Rx is a positive number, that means it points to the right. 7.464 meters is a lot bigger than 2 meters, almost 4 times the size. Okay, and so I'm not going to measure per se, but I do want to make a diagram that is roughly scaled. Okay, so that we can get an accurate picture of what's really going on here. So I'm just going to make a pretty big horizontal arrow for Rx. Okay, and I like to label it just because it makes it easier for me staying organized. Okay, and then Ry. Okay, a little bit smaller. So Ry is just that 2 meters. Okay, and so these components point up and to the right, so the resultant vector R also points up and to the right. Okay, so I'm going to go ahead and compute the magnitude of the resultant R here using Pythagorean theorem. Okay, which for this case is just the square root of Rx squared plus Ry squared. So just think this comes from a squared plus b squared is equal to c squared, where I would take the square root of my answer to get c, but I'm not talking about c, I'm talking about this resultant R here. Okay, so sub it in numbers. Rx is that 7.464 meters, so I would take that and square that, and I'm going to add that to my Ry, which is 2 meters squared. Okay, add that all up, take the square root, and you should get a value that is 7.2 or 7.727 meters. Okay, and this right here, this is half of the answer, because what I've computed is just the magnitude. Okay, vectors have magnitude and direction. Okay, so let me add in the missing variable. Okay, so that's my theta, that's for my direction. Now I have all 3 pieces of the triangle. Okay, so really I could pick any of the inverse trig functions that I wanted. All right, but I think in this case I'd have a tendency to stick towards tangent if I have the 2 side lengths of the triangle. So I'm going to go inverse tan. And if you remember from SOHCAHTOA, tangent would be opposite over adjacent. So for this case, opposite of the angle is Ry and adjacent is Rx. So staying consistent, inverse tan of Ry over Rx. I'm just going to sub in my numbers. inverse tan of our y, which is 2 meters, over our x, which is 7.464 meters. Okay, notice that in this case, because we've got meters in the top and bottom, the meters actually factor out, okay, which is a good thing. And so throw that in your calculator, make sure that you're in degree mode, okay, and you will find that this is an angle of 15.000 degrees. Okay, this second number, this is the direction. The r is the magnitude. Okay, and then before I go here, just a quick word on the reference of angles that WebAssign uses. Okay, in math class, if you've seen vectors before, vectors are typically drawn on the origin of the xy axis. So like our r vector here would point something like this, where our angle is 15 degrees. Okay, that 15-degree angle, okay, you'll see WebAssign likes to use this. They ask you to reference the angle counterclockwise from the positive x-axis. Okay, and so if this is the positive x-axis over here, it just says take your pen, take your finger, start it on that positive x-axis and go in the direction of counterclockwise until you hit your vector. And if that's the case, that's your angle. So just so you understand what I mean, let's just say for the sake of argument that we computed another vector, okay, that let's say that it pointed, I don't know, down here, okay? And again, this is just totally fictitious, just for talking points. Okay, well, in physics, we typically would compute, say, like this angle right here, all right, but in order to reference that for WebAssign, if it's that counterclockwise from the positive x-axis, okay, you still have to start on this positive x-axis and you go around all the way till you get to here. Okay, and that would be the angle that they wanted. So you might be saying, okay, well, how the heck am I supposed to get that? All right, well, if you've already got this piece here, this little green angle, okay, well, then really just think that there's just a part that's missing. All right, so to kind of go to here. So hopefully you see that that little blue arc is 180 degrees. So in this case, if your angle pointed in this direction, you'd add 180 degrees. So when you're doing these, picture, 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 picture. Okay, so like, you know, let me just do one more. Let's say our resultant vector pointed over here. Okay, well, WebAssign is going to want this angle counterclockwise from the positive x-axis. So that's what we're looking for is that red arc. And you say, how am I supposed to get that? All right. There's a real good chance that you computed that angle, in which case, just ask yourself, well, how many degrees is that? Okay, we know what that is. It's 360, and you've computed some angle, so you just subtract that from 360. Okay, so those are just some different ways to think about it. So just be aware of it, because that trips up a lot of students early on. Okay, so if you have any questions, all right, see your instructor. This is how we add vectors with the component method. Thank you.